So once in a while I bump into some good concepts like particle size distribution. Why particle size have to be distributed? That's a very good question to ask. See, when particles are forming, when you, for example, when you are doing a reaction, when particles are forming or molecules are crystallizing, you can never really control the size of the crystals. Therefore, you have to grind them to get desirable particle size. And you can control the molecules to form a particular size of a particle or particular size of a crystal if you want. So things exist in different kind of different particles exist in different kinds of sizes, and it's a very important bulk property which is going to affect your physical property of a particular matter. So in pharma field there are a lot of implications of a particle size distribution. We have to find the distributions of particle, how small and big a particle is in a particular matter, and what is the majority of particle size. In formulation, it plays a very major role. We are only desired to have a particular particle size, otherwise the dissolutions will affect, and a lot of physical properties of the tablet will affect. So it's a very important property in pharma. And also, so we have columns with different microns of particle size. So they give a fixed particle size like 5 micron, 3.5 micron. It's actually exactly not that particle size. It will be in a range. If you have a range of sizes is packed inside a column, if everything is uniform, there is no preference for a particle to move inside a column, for sunlight to move inside a column. But if you have a different range of sizes, sunlight will choose a path which is having they have preference for a path if you have a particle size difference inside a column. Therefore, the retention time will vary for each runs. That is not desired in a column. We need a reproducible retention times. Therefore, particle size needs to be uniform inside a column. And also, even taste of chocolates is affected by how well you grind that emulsion of chocolate emulsion. How well you grind it, the taste will differ. Like this, we can tell a lot of examples where particle size distribution is an important factor in deciding some things. So we measure the particle size. So small particles will diffract light, and based on a diffraction pattern, we can find what is the majority of size of the particle. We get a distribution graph. Actually, it's a Gaussian distribution. In analytical chemistry, a lot of things is a Gaussian distribution. For example, a peak, how sunlight is distributed inside a column. Many things are a Gaussian distribution. I will make a separate video about it. So we'll get a Gaussian distribution graph when you measure the particle size distribution of a particular sample. And the instrument we use is Malvern particle size distribution analyzer. The Malvern company have all instruments are produced by that company, and from an analytical point of view, the thing that decides the analysis is how advanced the instrument is. There is no analytical techniques much. If you have well advanced instruments, it's very easy to measure it. But in previous, there's some methods involve some analytical experiences needed involving some methods. But overall, it's more about the instrument that is measuring. We use a laser beam and we spread the molecule inside the chamber, and how the particles is diffracting the laser light. That decides from that we measure the particle size distribution. It's very the thing can be measured in minutes. So it's a very time less consuming process. So if you know about the particle size, you tend to see everything around you based on how particle size is going to affect a certain thing like that. So it's a very good concept, and I just want to share it.